Hello, and welcome everyone to our today's video presentation on the particle sum optimization algorithm.
So, what exactly is PSO, the particle swarm optimization algorithm? Originally attributed to three people, James Kennedy, an American social psychologist, Russell C. Eberhard, an American electrical engineer, and Shea, and was first intended for simulating social behavior as a stylized representation of the movement of organisms in a bird flock or fish school. Once the algorithm was simplified, it was seen to be performing optimization. Written by Kennedy and Eberhard, the book Swarm Intelligence describes many philosophical aspects of swarm intelligence. Later research by scientists led to the application of PSO in many optimization problems such as signal processing, combinational optimization, neural networks, trust optimization, and more. Talking about its characteristics, PSO is a meta-heuristic algorithm. It can search very large design space solutions with few or no assumptions. Although, due to its meta-heuristic nature, an optimal solution is not guaranteed. Thirdly, PSO doesn't require a differentiable optimization problem for its application as the gradient is not required, unlike the quasi-Newton method or the gradient descent method.
Now, you might be wondering how exactly does the PSO algorithm work.
It's a calm morning in the forest and a group of birds is looking for food. The birds do so by adhering to the steps of our algorithm, particle sum optimization. For now, instead of the whole group, let's focus on one bird in particular, Robin.
Here's our bird, Robin flying around and looking for food. To find the food successfully, all the birds in the group, including Robin, will follow three rules. First, each bird has to record the deepest path in the forest that they have followed so far. Second, before any movement, the birds needs to communicate so they can find out and update information about the deepest path that they have found so far, as well as the deepest path that has been traveled by the entire term. Third, each bird needs to know their current travel direction, which will allow them to find their next location. To move, each bird needs to fly 1 kilometer towards their current direction, 1 kilometer towards their personal base location, and 1 kilometer towards the flock base location. The blue rectangle shows the solution space in which our solution lies. In our case, the solution space being the forest and the solution being the location of the food. The screen shows the personal base location, base location, and current direction. The path followed by Robin, as per the rule, is shown by the black arrows and the resultant path by the green arrows.
Now, at the end of the hour, if Robin's new location is better than his personal best location, he needs to update it. If his new personal best location is even better than the flock's best location, he needs to communicate with the flock so the flock's best location can be updated. Let's say from the new location, Robin continues his journey and completes a total of 5 kilometers. And at the end, his path ends up looking something like this. We'd assume that every bird flies 1 kilometer each for personal best location, team best location, and current direction. We can vary this distance by the component 2r1, where r ranges from 0 to 1. The shaded path shows the area in which Robin may end up with every respective hour of journey. The red cross represents the food's location. Remember, there is a whole flock of birds looking for food here who will be following the same rule as Robin. At the end of every hour, the personal best location and flock best location will be updated. As all of these birds are following these rules, the probability of finding the deepest path or the food shown by the red cross is very high.
Now that we are through with our analogy for PSO, let's take a look at the mathematical model. As you can see on the screen, the position of bird or a particle is shown by x and y coordinates of the particles contained in a vector xi We can add more variable in the vector x to increase the number of dimensions. Of course, to update the position vector xi, we need to be able to define the particle's direction and speed using a velocity vector. The three factor that we mentioned earlier, uh, that current velocity, personal based and global based from this vector. For the second and third term, we need to calculate the distance to the personal based and global based respectively. Each term is multiplied by 2r to randomly increase or decrease its impact. By calculating the next hour's velocity, next hour's position can also be found by the relation shown on the screen. By using the velocity at the current hour, we can calculate the position in the next hour. As there are multiple particles moving through the design space, to update their position and velocity, two vectors are considered. The position vector describes the position of the particle while the velocity vector describes the direction and movement intensity. Both of these vectors are updated in each iteration of the algorithm. Our mathematical model differs slightly from the one is the analogy. First, instead of d, we have t or iteration. For iteration, next, current velocity is multiplied by variable called inertia. Last, c1 and c2 for the other two terms in the velocity vector. Inertia maintains the current velocity or current direction of movement. Components c1 or cognitive components it used to consider the distance between personal based and current location by a particle. Similarly, the component c2 social component is used to consider the distance between swarm based and current location by a particle. There is no subscript for g as a global based is only one quality. By by changing the parameters w, c1 and c2, we can tune our particles to explore in the solution space. Okay, so let's talk about them.
Here's a simulation of PSO with 1000 particles. With the parameter values shown on the screen, this is only to show you how the particles move in an ordinary condition with general parameter settings. As you can see, the parameters start from random position but converge towards an optimum point. Now, to test the effect of parameters on the search process, let us take the function shown on the screen. Okay, for the first search, the inertia weight is 0, 4% for the second one, and 10% for the third one. As you can see, for 50 generations, the first one shows very little exploration while the third one shows maximum exploration, visible due to the scattering of particles. Although in actual search using the PSO, the algorithm is modified such that the inertia weight changes during the search, which improves the odds of finding the global optimum. Now, let's look at the effect of cognitive or personal and the swarm parameter. Well, as you can see, in the first case where the cognitive parameter is 0, the particles tend to show more of a swarm mentality, preferring to move towards the global best and showing more convergence. However, in the second case where the social parameter is 0, particles tend to prefer searching in the region covered by their personal best, showing less convergence.
Well, before the example problem, let's take a look at the algorithm to better understand the computational functionality of PSO. Once we initialize the particles, the personal best for each particle is evaluated. If the current position is better than the P best, then P best is updated for the particle. And then the best P best value among all the particles is assigned as the G best or global best. After the global best is assigned, velocities are computed for each particle so their next position can be updated. If convergence is reached, then the procedure ends, otherwise it starts again from the top. For the final section of our video presentation, here's a numerical example. We need to maximize the given function with the given control parameters for only 5 swarm particles and in 4 iterations. Then, we need certain random numbers for updating the velocity. We'll use some random numbers shown in a matrix of 1 by 5 as there are 5 particles. So, for the first particle, the two random numbers are 0.4657 and 0.5319. However, the random numbers will remain the same throughout iteration, but in practical work, the random numbers may change with each iteration. Now, we'll initialize the fitness of all particles as zeros. The current position of the particles in the zeroth iteration can be taken as 10 times r1 minus 0.5. Then Cp0 is the current position of all particles. We multiply by 10 to initialize at least some particles to be above 1 and subtract 0.5 to get both positive and negative positions. Doing so will ensure that our particles cover different regions in the design space. Cp0 practically shows the x values. Similarly, the velocity is computed by R2 as shown on the screen. You can see how we obtained the velocities. Again, it's done to ensure that the velocity is not too low or too high and all the region is covered. Now, we have obtained the current position and velocity of the particles. For iteration 1, the current position of particles will be the one that we have initialized. For current fitness, we'll calculate the value of function at Cp1 which will give us the current fitness of particles in this iteration. Cp1 square is obtained by squaring individual elements of Cp1. So far, we have calculated current position and current velocity for the first iteration, which are the same as Cp0 and V0, and also we have found the current fitness for our particles. Now that we have the current fitness, our question is, what is the local best position? The local best position will be the same as its current position as we have nothing else in this iteration 1. So LBP1 will be CP1 and the same will apply for local best fitness which will be the same as current fitness. Now for the global fitness, as it's a maximization problem, the maximum one in our current fitness values is 1.0755, so we call it our global best fitness, as 1.0755 for fx has been obtained by x is equal to 0.0385. It will be the global best position. As we go to iteration 2, we'll apply the psychosocial criteria for velocity. The new velocity will have weight to the current velocity c1 and c2 along with random numbers lbp, cp and gbp minus cp. From iteration 1, we have V1 as well as the random numbers for the first particle shown on the screen along with Cp1, LBP1 and GBP1. For iteration 2, the velocity for the first particle can be calculated by inputting the above values. Now, we can follow the same process for finding the velocity of all the particles. We can find the next current position by adding the current position with the next velocity. Current fitness can be obtained by inputting the x values into fx. LBF1 values are shown on the screen, so what will be the LBF2 values? 0.5634 and 0.1976. The former is better as it's a maximization problem. Similarly, for 0.4250 and minus 6.7368, the former is better again because it's a maximization problem. By comparing the respective values of CF2 and LBF1 and taking the maximum value out, we can form LBF2. So only the fifth position is different between CF2 and LBF2. Then we can find out the global best fitness and global best position as well as the local best position. Now here's the tabulation of all the calculations as well as the equations. From the first table, you can see the global best fitness and global best position till the second iteration, and from the second table you can see the global best fitness and global best position till the fourth iteration. Here's the summary, the function for which we are trying to find out a maximizing solution. Theoretical values on the left and our calculations are on the right, and as you can see we have got a very close solution in merely 4 iterations. In fact, if we continue this process for a few more iterations, we may actually reach the theoretical value to a more greater precision. Thank you. That is going to be all for the video presentation. This presentation was made possible by the stock footages obtained from Pexel, which were recorded by HUF Allen. Renders that we made in Epic Games Twinmotion ourselves and MATLAB PSO code provided by Victor Martinez Gagigalou. Also, various educational sources such as Alil Mirza Alil's PSO tutorials and NPTEL PSO tutorials made this possible.